All right, let's start in our classroom. Everyone, laptops down, phones off, student IDs out, please. All right, we're starting. Gennaro is going to talk about something. Go ahead.
Thank you. So, okay, I think I didn't prepare any slides or anything, but I think I thought it is kind of important for us to talk about like big changes in an evaluation of a language. Now, one of the big changes happening in Racket recently was to move into the shade scheme runtime. And this is kind of a big change for a language, and I think it's useful for us to recognize and just it's create a discussion about why did this happen, and I think it's important for us to discuss this kind of changes in a language, and feel free to just contribute to, for instance, if there was a big change in GEC, I'm sure there are lots of big changes on that. But this happened to Racket really recently, the last year, and right now it is in progress. And I just wanted to let you guys know about what's going on in this setup. So the picture on the side shows the current Racket version 6, and this, let me just zoom in. Okay. Is it clear on that screen?
It's fine.
So the red part, the core is C, and the blue part is Racket code, and the red part is Scribble. It's a language on top of the blue part. So the goal is always, have Racket, improve Racket's code base, and it's not directly. The goal is not to have a faster Racket, but to have a better implemented Racket with an acceptable performance. And that means less C code, more Racket code in the implementation. So this part,
goal, first and foremost, is to shrink the red part as close to 0 as possible.
that is absolutely right. Yes, that's absolutely right. Because it makes sense, right? I mean, you want to have your core libraries and core language stuff implemented in your language, because you want your user and your developers to be easily able to contribute to your code base. Otherwise, they would need to write some C code, try to read all the.
So I guess I was surprised that he said that performance wasn't the absolute top priority and motivating this change. So
Right, no,
would the consequence of this be that we would consider trade-offs between performance and the normalized code in C?
Well, the first reason, I mean, the major change happened because they wanted to have more Racket code instead of C code, was to write the expander in Racket. If we just zoom into this red picture is the core stuff. That this red part is, you see this compiler plus JIT and expander was all in this C code, right? And you should have seen the implementation. It's just it was really messy. It just fused together, expander and compiler. It still is possible to run the compiler without running the expander and vice versa. But still, the code was really messy. And so what happened was, the last year was spent on writing this expander in Racket, turning it into blue, but the performance was full. So that's what actually partly the reason for searching for new runtimes, and shade scheme seemed to be a suitable thing. Is this the Ambrose? Is this the?
The red is what you've got left.
Okay.
Yeah.
So here's how Shea scheme looks like. There's a little kernel, and this kernel is in C, and this purple stuff is written in scheme, and the expander, the Shea scheme has its own expander, but it's just considerably smaller. This thing is annoying.
The ratio of C code doesn't look that much lower.
No, don't.
I'll take care of it.
Did you say something?
Oh, just the ratio of C code to scheme code doesn't seem that much lower there.
That's
The overall size of it.
kind of right. Yeah, let's look at the Racket actually. Racket has.
243K out of.
Yeah, you're right. The ratio is much more bigger in Racket. Yeah. And the expander, you see, there are a bunch of modules here that can turn into Racket code, which is like regex, IO, threads, control plus structs. So they're all right now actually written in Racket. So the Racket-onChez looks like this. Now there is this purple stuff is Chez's kernel structure, and this Rumble module is the new one that Matthew Platter and Sam actually helped to implement OnChez, and Rumble actually is there to support different runtime systems. Rumble is just connects this GC to control structs, or everything between GC and control struct. This built-in stuff contains all the data representation, the hash tables, or primitive data structures, fixed num, big nums, strings, characters, everything is built in. So the Rumble here, connects the Chez's representation of things with whatever runtime or whatever Racket implementation you want to use. So this RTT.io depends on something called RTT.io.c, which is kind of like a little the first layer above operating systems. That is about reading stuff, writing stuff, socket bindings, so it kind of has to be at C right now. So let's talk about a little bit of performance. These are just preliminary results, and you may recognize some of these benchmarks, and these are just classic Racket benchmarks. So you can see that Racket-onChez has a considerable performance right now, mostly because for instance, if you look at this, dynamic benchmark is a dynamic type inferencer. It defines a language, and there's a lot of cons-intensive operations. The problem with Racket-onChez right now is precisely the fact that Expander is written in Racket. Expander has in itself module system, microsystem, reader, eval. So Chez needs to Racket-onChez. The Chez runtime needs to load that expander and turn it into its own representation, which takes a lot of time, which is actually explained in the startup.
Well, but the mystery element to me here was, I read this blog post, and there's a schemify step. So there's this additional step that addresses these impedance mismatches between the scheme language and the Racket language. Things like forcing left-right word evaluation.
Well, schemify is actually about the linklets. The linklet stuff is, I'm sorry about the scrolling, sorry, I know it's annoying, but I want to just show you precisely the part that it talks about. Yes, the compiler plus JIT part is, it's below the module system. That's why writing expander and Racket actually separated the compiler and expanding business. Right now in Racket version 6, they're fused, the expander and compiler. So the compiler actually knows about module system, micro expansions, everything that the expander has. But in the new version, in Racket 7, expander is above compilers, is a compilation. That's why the compiler talks in terms of linklets, which are more primitive definitions. Is just the collection of lambdas, imports and exports some variables, and that's it. They don't even know syntax objects. They have like small syntax object like.
The way the expander goes from Racket service to Racket core, right? And then Racket core has to be schemified to map on to basically.
Schemify it's written in Racket. It's about expander in itself is going to create some linklets and use those linklets to expand stuff, work with it. And Schemify takes those expanded linklet representations in the Racket and turns it into whatever representation the runtime has for linklets. For instance, ShadeScheme represents linklets by functions. In Picket, we have a custom class for representing linklets. So the Schemify is the one who takes that linklet that the expander uses, the Racket's linklet, and turns it into runtime's representation for linklets.
But it doesn't turn it into anything that uses Shade's module system. It turns it into like a function, doesn't it?
Because Shade represents linklets with functions.
But what does that mean? A linklet imports and exports variables. Right?
That's true. The imports are the function. Imports are the function arguments, and the exports are the function's results.
Multiple values.
That's just an interesting representation of linklets. So, what are we doing on time?
You got about 8 minutes.
8 minutes.
Yeah.
Is the input to that function the imports and the output?
That's right. The linklet has its source, which has lambdas and imports and exports. But the use of linklet is by instantiating a linklet. So there's this thing called linklet instance, which is like the curried function, curried version of that function in Shade. It's basically you give another linklet instances as imports, and you basically instantiate every free variable that you see on those levels. So the startup on Racket Shade is the Shade's own startup plus the load time of expander written in Racket into Shade scheme's runtime. So, excuse me. So you can see that we have a little bit of a problem in Racket-onChez right now. It takes a lot of time. There's not much difference between this and that, the Racket-onChez and Racket-onChez /JIT. The /JIT Racket means that it doesn't compile whole linklets. It just defers the compilation of the linklet. It's basically compile only. It doesn't compile whole linklets. It just compiles lambdas when it needs to. It's gonna use them.
Is Racket 7 a work in progress version of the Racket source?
Sure. It's right now. Right now, the last release is 6.11.
So we can only really include this on the graphics because sites and differences in the way that Racket 7 works as opposed to Racket 6.
Right, right. But
The way the name would be that expander would be written in Racket, right?
exactly
Oh, right.
this startup, this original Racket startup is super fast because everything is written in C. The compiler, the expander, everything is in C. But this seems, I mean, this difference tells us that we have a bunch of places for improvement here. Just, because this is the lower bound, of course, all the time. So the last thing that I wanted to talk about was
This blog post is wonderfully quantitative, but the numbers I was really hoping for are not here. I wanted to see what the code growth size was.
sorry. Say it again.
The numbers I was hoping for are not here, I don't believe. I wanted to see what the code growth size was.
Well,
Because all this funny business trying to encode Racket-onChez, if it results into a large code explosion, then that can explain a lot of the increased startup times and everything.
you mean the difference between the implementation of expander in C and Racket?
No, I just mean Scheme is a different language than Racket, and there's some significant impedance mismatch in here. He mentions order of evaluation as one place.
Okay.
Yeah, left to right evaluation, right? So what? You expand every application into some chain of lets to force a given order. Now you're introducing that many more variable bindings. You're making code that much bigger. And it's not surprising that everything slowed down some. It's like other funny encodings where there's a semantic gap. Like when you target JavaScript from Haskell, you get pretty bad JavaScript code.
That's an interesting point because I was comparing this stuff with what we were doing on Picket. We were doing basically the same thing in Picket because it's just another runtime for Racket. But
But you designed it around Racket.
our luck is we're implementing a CEK machine, and we're implementing exactly Racket stuff. There's no semantic gap between what we're implementing and what we're getting from Racket. Sure. Yeah, my plan, our plan with Sam is right now to do the same thing on Picket, and I'm basically trying to load all the expander and
So
Racket.
like Racket 7 on Picket.
Exactly right. Yes. Right now, I'm able to load not Racket/base, but Racket private base on Picket's runtime, and means I'm using the Racket's expander, the expander written in Racket, to just bootstrap the Racket's own libraries.
So I know Picket is very slow to compile, but once it's compiled, what's going on at startup times do you get?
Startup time is still bad because it also depends on the JIT's warm-up time as well. There are different things to measure there. The JIT's warm-up time, the expander, the time it takes to load the whole expander, because the expander itself has like 3,000 function definitions inside. So it's just a big chunk of thing that we need to load every time we start up Picket. It's part of the boot. I can potentially.
You guys need saved heaps.
What's that?
You guys need saved heaps, like Shay used to have. Because the expander's never changing, so that whole first part of the process can be minimalized.
Right. I think I potentially can put it in the binary while compilation, but I'm not sure how to do that in our Python framework right now. But because it's a weird framework. But yeah, that's our plan is to right now to be able to load everything on Picket, and potentially my dream is to be able to run Dr. Racket on Picket, for instance, or Slideshow in Picket. So we'll see how the compilation affects affects these performance. I think that's all I have. I think
Is Racket-onChez actually compiling the expander every time?
True,
Or is it loading
this
the
is-
expander from
this is the let me just go back to yeah. These are all the blue parts are all the linklets that are exported statically from Racket to Che. So Che uses these to bootstrap Racket itself.
But when you measure startup time, those have to be recompiled from a .SLS or whatever it is every single time. They're not stored as binary on disk.
You mean these, the expander?
Yeah, like the Racket's expander can be recompiled, could be precompiled. to
That's true.
Racket-onChez.
That's absolutely right. I think that's what they're doing right now. But the startup time is. Oh, that's right. I think you're right. I may be mistaken about that. But there's also another expander in Che as well.
He says it. He says that it loads core boot files, and then time to load the expander. So that seems kind of unnecessary. I don't know why you guys make another boot file out of the expander. So maybe that's a place to improve.
Yeah, I think I should look into that.
No, it's okay.
And it's maybe
Actually,
another file.
just loading the pre-compiled .SLS.
All right.
Oh, no, not very significant.
So maybe he's talking about actually loading the pre-compiled version still.
That's a good point. It says time to load the expander. So you're right. The word load there is like time to load from source or load from backside.
Okay, let's thank Jeanette. Thank you very much.
It'll be okay.
All right, Praveen, there's nothing on your screen.
Okay. Yep.
Yeah,
I
you
know
did.
that.
Okay, take it away.
Alright, so my talk is going to be quite different from it's not a very formal talk or anything. I'm going to share some things that I've been thinking about recently, and you can ask questions whenever. I might pose some questions also. It's kind of a loose collection of ideas. You can find connections between them. We'll see. So today I'm going to basically be talking about generative art and more specifically generative music, because that's going to come out and know a little bit about it. And basically I came across this presentation recently which talked about this piece, which I will get to in a second, which started making me think about music and art as instances of some generative process. So, like for example, usually we have some piece by Bach or something that's written on musical notation, and usually that's a set of instructions, right? It's a program for people to play, and each performance is maybe slightly different. For people who have listened to this piece a lot of times, they might notice slight changes when the Cleveland Orchestra plays it versus when the New York Philharmonic plays it or something like that. So that's like one kind of variation from of the same piece of music from one instance to another. And then there are like pieces that are by design supposed to be different each time it's played. So for example, here's a piece. Okay, it's called In C. And this is really small, so let me make it big. And basically, what is in C like? So it's basically saying, okay, here are the instructions. Like, this is the entire, this is what's given to each performer of the song. And there's no rule in how many people have to play or like what kind of instruments they're going to be. So like roughly 30 or 40 people. And the instructions are, okay, so you have to start playing the riff. I'm going to call these riffs. And so you start playing riff 1 and you go all the way to riff 53. And you can take as much time as you want on each riff. It's up to you. Basically, it says keep looping the riff at least, not twice or thrice. But usually it's more than that. And these little melodies themselves like sound good together. But the thing is, really, it matters how and when people decide to switch from one riff to another, it decides how the piece sounds. So, for example, I can play some of these things, I think. Right, so that's just looping, it just sounds like that. And usually they go together. So. And it doesn't have to be that all the instruments are pianos or violas or something, they can be even percussion instruments, whatever. And there are different performances of this kind of piece. So, for example, here's a video I found performing this piece using a wide variety of instruments. So, yeah, I'll just let it wait for a little bit. You might hear some of the melodies I played earlier. Maybe I can even play it while this is going on.
Are you going to go forward or can you go back?
You only go forward.
Okay.
You mean like from
Like when you could repeat one rep, so you go, it's just you go back one. After finishing it, you can't go back.
when you can't, yeah. So people are looping like some people are just looping this one right now.
And then the instruments, the different people can go over at different rates.
Yeah, exactly. But the sort of general thing is there's a composer notes that they're able to do, but it's just like don't lag too far behind and don't go too far ahead. And some further communication. But other than that, just kind of like listen and like decide when you do. And the piece that ends when most people, like if you reach here, just like stay here and then you go like when everybody's reached there and then kind of crescendo and stuff. So that's kind of a process, right? It's a program, it's like, I think of it as a probabilistic program, which decides. Like, so the program is composed of all these little pieces and layers, and stochasticity or randomness comes in the choice of the layers to move forward or to stay. Okay, so if you put in a probabilistic program and each performance of this song is one sample from this code. It's kind of a something. And the piece does has a skill that it just to show you that it can change and create music. So you may want here so that's one example of sort of a piece of music that I thought was nice as to think of as a probabilistic program. And which made me think, okay, so usually when one writes a probabilistic program, like they use little blocks like we saw earlier, all those little melodies. The blocks in a probabilistic program are usually like primitive distributions, like normal or song or whatever. And you have graphs that describe what these distributions are supposed to represent, which is fine, but when I compose that into a big program, I don't really know what that big program represents. I kind of don't have an intuition for it. But if I change my coordinates, right? If I think about my program producing music instead, I actually do have an understanding of the music as a whole much better than I do of like a probabilistic program that just produces static numbers. So that's something I started thinking about. Like we do that in a natural way in math too. Like we try to think about one problem in terms of some other theory, right? Like people like category theory, for example, in order to interpret something from AI or something like that. And it's just making me think like how, I don't know, here's a question for the audience, right? Like, what are examples when you have thought about the same problem and using completely different field that has helped you like gain better intuition for this thing? So that's something I wanted to pose as a question. All later. I will move on and I'll show another example of generating music with different kinds of music with the same program. So another composer, he sort of started this technique called phasing. So the idea there is that two people play the same thing, but one plays it slightly slower and the other plays it slightly faster. So initially it sounds like they're playing the same thing, but slowly they go out of phase and they come back in phase. And this coming in and going out of phase creates different patterns. The composer didn't actually manually compose, he just like made a program that and then generated music. So for example, I think here is one. So this is a nice visualization that helps you see what I just said. So that's one riff. Now two people are playing that same riff, but one's playing it at a slightly different speed. Both these melodies are very simple, so like it's repetitive or like you can see that they're differing and they're creating melodies in the pattern. I find it interesting that some people think it's too simple, case thing, but it becomes interesting. This sort of programming the music becomes interesting when you add a lot of instruments and a lot of structure to it. So here's a piece that I this is an excuse basically just for me to play this, which employs this technique, and I think it's really cool. It's much harder to actually simulate this piece but the piece does progress, and people are playing similar riffs, but because they're playing sometimes at slightly different speeds, you hear the others coming out. So, just going to jump to a random portion. And coming back to the idea of visualization helping you, this is again in the same vein of how will you look at the same problem in a different way, and it helps you understand. Often I don't really like a song, and I see someone like dance to it or something, and now I really like the song because I saw sort of visual interpretation of it. And here's an example of that I thought was really cool, where, I mean, this is already a song that I think many people have heard, and it's kind of pleasant, and I already liked it, but it gave a different interpretation of the song. So this is I think some cello suite by, you recognize it, right? Nice. change these strings and record times, and if I choose a different set of, different set of choices, it will keep everything else fixed. And if I make it a different melody with the same rhythm and cadences of this song, it will be something like main harmony of different things. And like, so thinking of the what we have already in terms of
I'm kind of having a hard time connecting the probabilistic part of this. I mean, you still have the same distribution. You still have the same. The thing that you just said, you just change one thing, everything else is the same. So what exactly do we get? I'm trying to connect these two aspects, probabilities, and
There's
this.
like different performances.
Yeah, okay, so maybe it's easier to look at this one. And I think in my head I know what I'm saying, but maybe it's not that sharp. So in this situation, like, say there are just you and me, just two people playing this piece. And we start playing at measure one. And you were the first one to decide to move to two, but I decided to, for some reason, stay at one for a while. So that was a choice you made. But tomorrow the choice could have been different. Like tomorrow maybe I would have moved before you did, or something like that. So there's in each performance there's some randomness in like how the piece moves forward, and yeah, the randomnesses cause different songs to come out. Basically.
It feels like a more a different way of rolling a dice. Know what I mean? It's just it is based on the non-deterministic behavior of people. It depends on how we're feeling. Just the playing the stuff. It just depends on a lot of things. So.
Like maybe I don't get along with you, and I want to keep playing on top of
Right,
what you're playing.
right.
So then like anytime you change, like I'll change also. And play like
Right.
so,
Yep.
Very nice.
Okay, great. I think, let's see, what else can we talk about? So, I found this really old sort of graphical DSL for making this kind of generative music. Here the idea is that it gives you, there's the 12 sort of algorithms it gives you based on which it produces patterns of tones. And so basically here are the primitives of this language. The constructs are these algorithms, how many, what voices you can add, and how long you can loop them for algorithm and stuff. And it's a composition tool, which allows you to write different programs, which are basically different selections of these choices. And then based on that, it will generate. There is randomness, like I think some of these sequences, yeah. But anyway, I thought it was interesting because I know there are a lot of DSLs for making music or like stream processing related DSLs in Haskell. And I see a lot of them at the farm workshop at ICFP, but I haven't really looked at all of them. I just found this one. I don't think anybody's ever looked at this one before, so I just thought I'd put that out there. And there is actually a lot of work these days with neural nets and generative music. And this is just another point of the spectrum. I don't know how it relates to what I'm thinking about. But here the idea is that you learn a certain style. So you listen to a lot of like, Mozart, or you listen to a lot of death metal, and you learn, so the neural net learns some representation of what it means to play Mozart. And then it's basically learning a marker chain, kind of. So, and then you use that representation to produce, randomly now produce things that copy the sound, basically. And I'm not sure how it really sounds, but here's a situation where, like, in the previous pieces that we heard today, there was a human who actually composed that representation, composed that program, which then produces different sounds. But here, I don't think there was that much control over that. Let's see, what is this? Actually, this is from it's from 2002. I think this is supposed to be better. Like show more. It's not zero else. Mostly, I wonder, like, they're obviously showing us the best output from this. I'm curious about the stuff that doesn't sound like it. Anyway, I don't know if there are any questions, but let's start with this one.
So I think this is a really interesting discussion piece because it ties together kind of different areas of computer science, but also humanities and music and that kind of stuff. And one of the reasons, or one of the things that kind of points to that is there was multiple episodes of Star Trek about Data learning to play music. So it's something that people have been thinking about, and I find that interesting. I also find it interesting that we tend to change how we talk about things based on what's big or popular in our field at the time. So now machine learning is very big and popular. I was wondering if you looked at like kind of older stuff for music generation, and if there had been like a big change in how people approached it. Were older systems very, I will lay out these blocks and then connect them, and then you'll have probabilistic transitions. Like, was there now a more focus on, actual probabilistic descriptions and neural networks? Or how has the conversation changed about this?
Yeah, I know that like when generic algorithms like first came out, they were pretty big. People tried to use generic algorithms to I'm sure Wikipedia has more information on that.
But have you noticed like a big shift in how people are trying to do this? Because it seems like it's very, humans play music, computers should be able to play music, so we're trying to get the computer to do it. But have you noticed a big change in how people are trying to do it?
No, I don't know. I'm not like I would imagine that using algorithms or ideas from mathematics and trying to generate music from those ideas. People are using like fractal processes, like that DSL that I showed you. All those algorithms are actually different kinds of strange and fractal chaos that generate patterns, and so like, people try to create music directly from.
It's just interesting watching one group of computer scientists go, "Ooh, look at this new cool toy," and everyone go, "Ooh, let's see if we can put that toy in our thing."
All right, it's 5 o'clock. Let's thank Praveen.